There are two special cases that I want to talk about now when we're dealing with combining random variables. Here's the first one. A college uses SAT scores as one criterion for admission. Experience has shown that the distribution of SAT scores among the entire population of applicants is such that the SAT math score X has a mean of 519 and a standard deviation of 115, and the SAT verbal score Y has a mean of 507 and a standard deviation of 111. What are the mean and standard deviation of the total score, X plus Y, for a randomly selected applicant to this college? Well, we know that the mean of X plus Y, and this is another way to write that, mu with a subscript X plus Y, is equal to mu of X plus mu of Y, which is 1026. We also know that the standard deviation of X plus Y, is never equal to the standard deviation of X plus the standard deviation of Y. We can never add standard deviation. So never add standard deviations. We can only add variances. Okay, so we could write this. The standard deviation of X plus Y is the square root of the sum of the two variances, because remember, variance is standard deviation squared, which would be 115 squared plus a 111 squared, and take the square root. But this is true only if SAT math and scores are independent. Well, they're not. They're not independent, because let's think about the probability of, say, well, I'm not going to write it out in terms, but let's say the probability that you get a high score in math is probably greater if you've also gotten a high score on the verbal side, and vice versa. Because a student who scores high in one category is more likely to score high in the other, because maybe they're farther along in school, they've had a better background educationally, they're overall just more intelligent academically, because there's lots of different kinds of intelligences. But anyway, it's very unlikely that these are totally independent of each other. So because they are not independent of each other, then that means we cannot add the variances and we can't find the standard deviation. So we can't go any farther with this problem in AP Stats. Now, in statistics in general, if you took a higher level of statistics, there is a way to deal with this. And for those of you who have had pre-calc, let me just tell you that if you think about the Pythagorean theorem, and then you think about the more general case, which is the law of cosines, just like the Pythagorean theorem is a special case of the law of cosines, this process that we're doing in AP Stats is kind of the simplified version. There is something that sort of loosely corresponds to the law of cosines in statistics that allows us to deal with non-independent variables when they are combined. So I'm going to erase this now because it doesn't really fit on the notes, but there is a way to deal with this. Okay, now back to the dice again. Okay, so I want to talk about another situation. What if instead of rolling one die and using one score distribution and the other die and using a different score distribution, what if we use the same score distribution for both die and we roll the die twice? So here's what I want to point out. If we're doing the expected value of x plus x, is x plus x equal to 2x if these are random variables? No, it's not true. The algebra of random variables is a little different, because the two x's represent two different dice rolls with two potentially different outcomes. So x and x might not be the same number. If I rolled a 1 and got a 0 score out of that, and then rolled a 6 for my other roll and got a 50, x plus x could be 0 plus 50, or x plus x could be 0 plus 0, or 5 plus 50, or 5 plus 0. So there's all different combinations of x plus x. So x plus x does not equal 2x in random variables. So we treat them as two separate random events. So let's call roll 1 x sub 1 and roll 2 x sub 2. So what we're really finding is the expected value and standard deviation of x sub 1 and x sub 2, roll number 1 and roll number 2. Well, we know they both have a mean of 10, so their expected value of the sum would be 20. They both have variances of 325, so there we can add variances because these are independent events. Yeah, so I should probably write that down. Independent. So let me write it down a little differently here. So we know that x1 and x2 are independent because they're both dice rolls, so they are independent of each other. We know that. Okay, so we can do that, which means then that the standard deviation of x1 plus x2 is the square root of the standard deviation squared, which is, of course, the variance. So we could have actually written 325 plus 325 here, really, since we already knew variance. And that would be that same number we got before, 25.495. So what if we play the game 10 times? Does this extend? Well, yes. This time we'd be adding up the expected value 10 times. So we would have 10 tens, or 100. If we added up the standard deviation squared 10 times, we could write that as 10 times 18.03 squared, and then take the square root of that. So this would extend to as many times as you want to play the game, or as many times as you want to repeat that random variable.